In section 13.2, we're looking at limits and continuity. This slide shows the definition of a limit of a function of two variables using the delta epsilon definition. Take a few minutes to look that over. For functions of a single variable, the limit exists if the limit from the left is equal to the limit from the right. For functions of two variables, however, the limit exists if the limit from all possible paths are equal. That is going to present us with a challenge. Going in two directions for a function of single variable isn't too bad. You can go from the left or from the right. But in terms of functions of two variables, there are an infinite number of paths. So that could, again, present us with a challenge. For some functions, it's easy to recognize that a limit does not exist. This example, find the limit as xy approaches 0, 0 of the function 1 over x squared plus y squared. If you plug in 0 for x and 0 for y, you will get 1 over 0, which is undefined. So we say that the limit does not exist. On the graph, as you approach 0, 0, this graph goes all the way up to positive infinity the closer you get to the z-axis. So the limit does not exist. You can also find limits using direct substitution. Go ahead and plug in the values for the x and y given for these, and then come back and check your answer. The first one is given already. Find the limit as xy approaches 1, 2. You're plugging in 1 for x and 2 for y, and by simplifying you get 2. So we can say that the limit of this is equal to 2 by direct substitution. Let's look at the next two limits. Find the limit as x approaches 0, 0 of 5x plus y plus 1 equals 0 equals, and find the limit as xy approaches 1, 1 of x over the square root of x plus y. So by direct substitution, for the second one, the limit as xy approaches 0, 0, plugging in 0 for x and 0 for y, and simplifying you get 1. So the limit of that function of two variables is equal to 1. Let's do the same thing by direct substitution, plugging in 1 for x and 1 for y. We get 1 over the square root of 2, or if you rationalize the denominator, the square root of 2 over 2. That's the limit of that function. For this one, we want to find the limit as xy approaches 0, 0 of x over x squared minus y squared. When we plug in 0 for x and 0 for y, we get a 0 in the numerator and a 0 in the denominator. This is an indeterminate form, meaning you cannot determine the limit simply by plugging in the numbers. So you have to look at this in other ways. One way is by looking at it as you approach the point 0, 0 from the path y equals x. We're trying to get close to this point 0, 0. There are many ways of approaching this point. One path that we're going to be looking at as you approach the path from the line y equals x. This can then be simplified to, we can look at this numerically, looking at a table of values, plugging in points, and examining what happens to the value of x over x squared minus y squared as you get closer and closer to the point 0, 0. We can say start off at the point right here at the point 1, 1. You can plug in 1 for x and 1 for y, and you get 1 over 0, which is undefined. Okay. As you get closer, say at a point 0.5, 0.5, again, you get 0.5 over 0, which is undefined, or it goes to infinity, but we could say undefined. And the closer and closer you get to 0, 0, you can see each of those values is going to be undefined. So we can say that in this case the limit is undefined because we're looking at this from the path y equals x. We could say that the limit does not exist, or dn E. Okay, let's look at another one. Let's suppose we want to find the limit as xy approaches 0, 0 of y over x squared plus y squared. We can approach this from different paths and determine what the limit is, or if the limit exists at all. For example, one path, and you're approaching the point 0, 0. One way to get to the point 0, 0 is by using the line y equals x. But let's look at another path, y equals 0. The path y equals 0 is the horizontal line that goes through 0 on the y-axis. So you want to get closer and closer to the point 0, 0 from this path. If you do this numerically by making a table of values, say look at this point on the path is 1, 0. Plug in sorry. So at the point 1, 1, sorry, 1, 0, at the point 1, 0, this becomes 0. You make a table of values. You get closer. At the point 0.5 comma 0, here we get, again, 0 again. So as you get closer and closer to this point, it appears that this limit is going to 0. You can do this algebraically as well by making substitutions. Find the limit by making the substitution on the path y equals 0. You're going to replace the y in the whole limit with 0. Find the limit as x0 approaches 0, 0. All right, sorry about that. I rewrote it to make it a little bit clearer. Looking at it numerically from this path where y equals 0, starting at the point 1, 0, you plugging it in, this path is going closer to 0. Algebraically, if you take this limit and replace the y with 0, you get the limit as x0 approaches 0, 0 of 0 over x squared plus 0 squared. 0 over x squared plus 0 squared can be simplified to 0. So now we could say the limit as you approach 0, 0 on this path is equal to 0. Now that does not say that all of the limits will approach 0. We're just saying that in one direction we find a path that approaches 0. That doesn't mean that we have all directions. So let's look at another path. If both of these paths go to the same point, we can say, okay, those two paths work, but are we looking at all of them? No, it's really what we're trying to do here is find two paths that will approach different values. And if they approach different values, you can say that the limit does not exist because it has to go to the same thing from all paths. So let's look at the path y equals x. From the path algebraically, from this path, we can do substitution here. The limit as xy, I'm going to replace the y in the equation with x. The limit as x comma x approaches 0, 0 of replacing the y with x in the numerator over x squared plus x squared, replacing those x's. Let's simplify here first, and we get the limit. Since we only have one variable here, we can change it to a limit of a single variable of x divided by 2x squared. And this can be further simplified to the limit as x approaches 0 of 1 over 2x. Now if you plug in 0, you get 1 over 0, which is undefined. So if the limit going from the path y equals 0 approaches 0 and the limit going to 0 from the line y equals x approach two different things, one goes to 0 and one is undefined, we can say that this limit does not exist. That would be our answer because we found two paths that approach different values. One goes to 0 while the other one is undefined.